This week we're going to look at higher order derivatives, implicit derivatives, and derivatives at a point. Now the first one here, we're looking for the third derivative. We don't very often go past the second derivative, but I still wanted to do at least one example. Now before I even take the derivative of something like this, I like to rewrite it so that we don't have any fractions or radicals. Then we can take the derivative. Now the first derivative, you're going to do 4 times 6, which is 24, x to the fifth, negative 2 times negative 1, which is positive 2, x to the negative 2, 24 times 5 halves, which is 60, x to the 3 halves, plus 19. Then we can do our second derivative. 24 times 5 is 120, x to the fourth. 2 times negative 2 is negative 4, x to the negative 3. 60 times 3 halves is 90. X to the 1 half. Third derivative. 480 x cubed plus 12 x to the negative 4 plus 45 x to the negative 1 half. And then we just simplify. This example, we're going to find the second derivative. First derivative, we just use the chain rule. So 2 times 6, x cubed plus 1 to the fifth, derivative of the inside, 3x squared. Now we can simplify before taking the derivative, so 36x squared, x cubed plus 1 to the fifth. But when we go to take the second derivative, we aren't just using the chain rule anymore, we also have to use the product rule. So derivative of the first, rewrite the second, plus the first, and then use the chain rule to take the derivative of the second. Simplify. Again, we're going to find the second derivative. To find the first derivative, we're going to use the chain rule, the quotient rule. So derivative of the top, bottom, minus the top, derivative of the bottom, over the bottom, squared. And simplify the top, giving us 24x plus 40 minus 24x over 3x plus 5, which is the same as 40 over 3x plus 5 squared. You'll notice there's no x's in the numerator now, so I'm going to rewrite it like this, so that when I go to do the second derivative, all I have to use is the chain rule, because quotient rule will be a little bit more complicated than needed. So here we get 40 times negative 2, 3x plus 5 to the negative 3 times 3. Simplify, we get negative 240 over 3x plus 5 cubed. Now let's do some examples of implicit differentiation. As you can see here, we don't have a single variable isolated. That's why we call it implicit. So here we're going to get 4x cubed. We're going to have to use a product on this next part. And because of the subtraction out front, I'm going to put it in brackets. So derivative of 5x squared is 10x. Rewrite the y cubed plus 5x squared. Derivative of 3y cubed is 3y squared. dy dx equals 3x squared plus 4y dy dx minus 9. Now the biggest thing with implicit is whenever you take the derivative of a y, you need to multiply by dy dx. Now we can simplify. 4x cubed minus 10x y cubed minus 15 x squared y squared dy dx equals 3x squared plus 4y dy dx minus 9. Now we want to isolate and find dy dx. The easiest way here would just be to move the 15x squared y squared to the right and everything else to the left, giving us all our dy dx's on the right hand side. Then we can rewrite the left side. Factor the dy dx out, and then divide, giving us our final answer. In this example, we have the chain rule along with implicit differentiation. So 5, 2x minus 3y to the fourth. Derivative of the inside is 2 minus 3 dy dx equals 0. Now because it's equal to 0, we can divide both sides by the 5, 2x minus 3y to the fourth, just leaving us with 2 minus 3 dy dx equal to 0, which is so much easier to rearrange. Giving us a final answer of dy dx equals 2/3. Now this question is very similar to the last one, but it's actually quite a bit more complicated. One, we have a product within the chain rule, and two, the right hand side isn't just equal to a constant, so isolating dy dx is going to be a little bit more work. So we still start off the same, for 1 minus xy cubed. Then we're going to use the product rule in here. Now, for emphasis on derivative of 1 is 0 minus, now because of the subtract, we have derivative of x is 1, so y plus derivative of y is 1 dy dx equals 2 minus 3 dy dx. Going to do an extra simplification step in here. So we have negative y minus x dy dx. Now, because we have that dy dx inside of a bracket over here, you're going to find you want to take this whole term out front and multiply it by each term inside. This will end up giving us negative 4y 1 minus xy cubed minus 4x 1 minus xy cubed dy dx equals. Now we need to isolate dy dx. I'm going to move the 3 dy dx over to this way, making it positive. And then we bring the 4y 1 minus xy cubed over to this side, making it positive. There are other ways to rearrange. I'm just trying to keep things as much positive as I can. We can factor out a dy dx. And divide. Now let's do a couple where we're evaluating derivatives at points or at values. So this one here, we take the derivative, 3x squared minus 2x, and then we're going to plug in the point. Now, in this case, we only need to plug in the 4. So we get 3 times 4 squared minus 2 times 4, which ends up being equal to 40. Here we need to find the second derivative and then plug in the value of -2. So we use the chain rule. We can simplify. When we go to take our second derivative, we now have a product. So derivative first, rewrite the second, plus rewrite the first, chain rule to take the derivative of the second. We can simplify. Now to evaluate the second derivative at -2, careful with the negatives. You should get 5800 when you put it in your calculator.